Hello everyone, and welcome again to NEDL, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and we would also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and we're going to investigate the Logit model, or as it's also called, the logistic regression. It's a go-to technique for estimating regression models when your response variable, so your dependent variable, your y, is categorical or binary. Often, in finance and economics, you have got your dependent variable being not a real number, but a categorical number. So it can only be 0, 1, or can only take some limited number of outcomes. Most importantly, and some of the most important applications of the Logit model are credit scoring, predicting whether your borrower would default on their debt, well, 0 being a non-default, everything goes according to plan, and 1 being default, and you are pretty interested in figuring out which characteristics of your borrower predict defaults, so you could allocate lending as a bank more efficiently and minimize your credit risk. Alternatively, in economics, you can be interested in predicting recessions, 0 being no recession and 1 being recession, and figuring out which macroeconomic or some other indicators perhaps can forecast recessions. Also, quite a legitimate research task. Or in education, we might be interested in what predicts or determines success or failure in an exam. How does the number of hours studied in preparation to an exam contribute to success rate? And all of these questions are also legitimate and can be answered using the Logit model. So without further ado, let's try and estimate the Logit model on a very textbook case for its application. That is credit scoring and predicting retail loan defaults. So here we have got a sample that's a real-world testing data sample of 500 applicants that either defaulted or haven't defaulted on their consumer credit. So we have got zeros denoting non-defaults, so the individuals repaid their debt, and ones being defaults. So here you can see that among the 500 individuals that have applied for the loan and being granted the loan, 127 have defaulted. And that's quite important for our binary choice models, Logit included, to be functioning properly. You need a sizable chunk of your sample to have either zeros or ones. If the overwhelming majority, like 95% of your sample being either 0 or 1, so if almost everyone have repaid or almost everyone have defaulted, then the Logit model would have been not the best choice. However, here, as we've got roughly a quarter of our sample defaulting, Logit model is appropriate. So that out of the way, we can study other variables that we've got here. So the two most important, perhaps, categorical variables that you could ask for when deciding whether to grant someone a loan or not is to ask if they have got any retail property on their hands, whether they are a homeowner or not, whether they can pledge their property as a collateral perhaps for their loan, or whether they have such property as an asset that could back them up if they encounter some difficulties in repaying, and also whether they have a full-time job, so whether they are full-time employed. And those two variables are, again, binary variables that are treated here as independent, as predictors, as explanatory variables for our y, which is default or not. And we have got also some real numbers as our explanatory variables, and we'll try and transform them into some predict that we could later use in our Logit model. So we have got income and expenses of our borrower's household in thousands of dollars per year. So we can see that this particular household earns roughly $129,000 a year and spends $73,000 out of that. We can also record the assets and debt right now before the loan is granted of this particular household and the amount of the loan they're asking for. So this data can be then coded into other explanatory variables that we can later use in our Logit model. So first of all, let's consider three variables that transform our income, expenses, asset, debt, and loan amount data into some more interpretable indicators. For example, we can figure out the natural logarithm of the ratio of expenses to income and figure out how thrifty, how likely to save their income this household is. And we expect that the more they save and the less they spend, the more likely they would be to repay their loan, as they would be more disciplined, they would have more spare cash to meet their monthly payment schedule, and so on and so forth. So this is a legitimate variable to consider. Then we can consider leverage, as in debt to assets, like we do for corporate analysis, but here we've got individuals and their outstanding assets and debt and the debt that they're planning to take. And they plan to fund some asset purchases with such a debt. Perhaps they want to buy a new house or a new car or the like. So here we can figure out natural logarithm. This is just for scaling purposes, so that we have got no outliers at the top. So we can figure out the natural logarithm of the leverage of our applicant after they would have been granted the loan. So in the numerator we would have total debt, which is outstanding debt, debt before they were granted the loan plus the loan amount, divided by their assets after they were granted a loan. So assets plus the loan amount. Here we assume that they'll spend the loan amount to purchase some assets for themselves. And here we can also figure out one further variable that would basically mean how long would this individual need to keep earning to repay their loan. And that can be calculated as the natural logarithm of the loan amount over their typical income. And here we have got 5 explanatory variables, which is more than enough for a typical Logit model, especially with 500 observations. So here we can bottom calculate all the way down and now start figuring out how to calculate the optimal values of these parameters, which denote just the constant term, as in all regression models, and our coefficients for our explanatory candidate variables. In the Logit model, what you utilize is the odds ratio, and you try and estimate the probability of default conditional on these values of explanatory variables. And as it is also called the logistic regression, it should not be a surprise that the equation that relates the predicted values of y, the variable of choice, the probability of default, utilizes the distribution function of the logistic distribution. And we have got a video on the logistic distribution on our channel already, so please check this out later on if you're interested. So here we use the logistic distribution logic to relate these variables. They can be anything, they can be bounded or unbounded, they can be categorical or real numbers, and so on and so forth. So we basically scale them to meet the criteria that the probability can be estimated from 0 to 1. And this is what makes logistic regression and Logit more applicable to categorical variable modeling than, for example, just multiple linear regression. Because in multiple linear regression, you can theoretically get estimated values of your dependent variable outside of 0 to 1 bounds, and that could be tricky to interpret it in context of probability of default, for example, or probability of recession, or probability of failing or passing an exam, and the like. This transformation, the Logit transformation, allows to avoid that. So here we can calculate the Logit, which is just the exponent of the weighted sum of our explanatory variables and the coefficients. So we can use sum product and refer to our coefficients over here and lock in the row as coefficients stay the same for all observations, and referring to explanatory variable plus a constant for simplicity over here corresponding to a particular observation. And here we calculate the value of Logit, and unsurprisingly, as all the coefficients are zeros as for now, the value of Logit is 1, as the exponent of 0 is 1. And here we can use this logistic transformation to convert this Logit value into our estimated probability. So we just divide our Logit by 1 plus Logit and get a default estimated probability of 0.5, which is unsurprising. If you know nothing about it, you can just assume it's a coin toss. It's 50-50, either you default or not. Quite intuitive, isn't it? And then we can bottom right click it all the way down and estimate it for all of our observations, all of our 500 loan applicants. And here it's actually important to understand how one might optimize these coefficients to arrive at the best fit possible. And here is where the Logit model differs from multiple regression in terms of the function that you try and optimize. For multiple regression, you try and minimize the squared sum of residuals, while for the Logit model, the most robust approach possible is to maximize log likelihood. And the log likelihood is defined in terms of actual variables, actual dependent variables that are zeros and ones, yi over here, and the estimated values, the expected values of yi, denoted here as y bar. And we can estimate our log likelihood for every single observation by just multiplying our default categorical variable onto the natural logarithm of our estimated probability plus 1 minus the default categorical variable times the natural logarithm of 1 minus the calculated probability. And we can bottom right click it all the way down, and then we can calculate the total log likelihood, which would be the sum of log likelihoods across the whole sample. And now we can maximize our log likelihood by varying the coefficient parameters. This can be done using solver, so we can go data solver and specify our optimization task. So we want to maximize the value of log likelihood, currently at cell L1. We want to maximize it, so here should be max, and we need to change variable cells that correspond to B0, B1, all the way to B5, that are the constant term and the coefficients for all 5 explanatory variables. So we select the array C2 to H2. And we don't want to impose any constraints on our parameters, as theoretically any of these parameters could impact probability of default either positively or negatively. We just have some reasonable suspicions whether, for example, leverage would affect the default probability positively or negatively. But the whole purpose of Logit estimation is to test these suspicions, these hypotheses. So we need to untick this box to make all parameters either positive or negative, depending on what maximizes log likelihood, and click solve and wait until the algorithm converges to an optimal solution. And we can see that we have converged to an optimal value of log likelihood. We can see it increased from roughly minus 350 to minus 233. Here the negative value of log likelihood should not be of concern. It doesn't really matter whether it's positive or negative. It only matters in comparative terms, whether it have increased or decreased, and we can see that it increased quite a lot. And here we can already see what the optimal values of coefficients are, the closest values to some true parameters that could be possibly estimated using maximum likelihood. And here we see, quite unsurprisingly, that being a homeowner and being full-time employed reduces your probability of default, makes it more likely for you to repay the loan on time and in full, which is, again, quite intuitive, while being more careless in your spending habits, spending more in proportion to your income makes you less likely to repay, being more leveraged makes you less likely to repay, and also taking on higher loan with respect to your income also makes you less likely to repay and more likely to default. All of those relationships are quite intuitive in terms of the logic, either psychological or economic, of the theory that is behind it. But now we need to figure out which of these relationships are statistically significant and reliable, and which are perhaps not significant and can be neglected in further modeling. So here we need to use some procedure perhaps to estimate the variance of our estimator to come up with standard errors for our coefficients, just as we do with multiple regression. However, here, just as with log likelihood, instead of minimizing squared sum of residuals, we have got a slight tweak on the conventional procedure of estimating the variance of our regressors, and we have got it covered over here. To estimate the covariance matrix, the variance of estimator of B, we need to calculate the inverse matrix of such matrix product that has the transposed x, the transposed matrix of our explanatory variables, including the constant, multiplied by the weight matrix, and weight matrix will be explained a little bit later, so stay tuned. And again, finally, the matrix of x as in explanatory variables again. And what is the weight matrix? Well, the weight matrix corresponds to the variance of individual probabilities. And here is actually one of the another reasons why Logit model is preferable to linear probability models when you just regress your zeros and ones in a multiple linear regression. As if you recall, in a binomial distribution, when you have some probability that an event happens and some probability that doesn't happen, the variance of the probability can be defined as probability times 1 minus probability. So basically, in such a categorical variable estimation, your data is heteroscedastic by definition. You have got different variances for different observations. So, for example, here, if you were to regress it using the usual method, the simple multiple linear regression, you would have assumed, as per the Gauss-Markov assumptions, that variances for all these observations are the same, while in fact they can be massively different and depending on the value of the estimated probability. And the highest variance of probability would be observable for the estimated y being equal to 0.5, as is usually the case, as is always the case with the Bernoulli distribution. So here we need to calculate the weight matrix, that would be the weighting matrix of our variance estimator, based on the diagonal of our probability estimators. So here we have got the template to calculate the 500 by 500 weight matrix. And here we need to first figure out whether we are on the diagonal. And if we are on the diagonal, we need to input this particular variance estimation. And if not, we need to input 0. So first we check if the column indicator and row indicator are the same. We can input the product of probability, and we need to lock the column here, times 1 minus probability. Locking the column here as well. And if not, if we are not on the diagonal, we just return 0. And here we can use Ctrl right and bottom right clicking it all the way down. We can calculate the whole weighting matrix. And we can see that on the diagonal we have got variance estimators, them being quite different and being the highest, the closest they are to 0.5 as expected. And now I can finally calculate our covariance matrix that we can then be used to derive standard errors of our coefficients. So here we first need to input min-verse, which is inverse matrix. Then we first need to input our mmult function, so matrix multiplication. The first component would be the transposed array of explanatory variables x, starting from the constant all the way to here, so it would be a 6 by 500 array. And as the second component, we input another matrix multiplication, and here first we input our weight matrix, so from here all the way to here, so a 500 by 500 matrix. And as the second component in this particular product, we'll input our x, and we don't need to transpose it at that particular point. So we close all the parentheses and make sure that we close them all, and then enforce this formula using Shift-Control-Enter as it multiplies a bunch of matrices together, basically. And we get our covariance matrix. And now, on the diagonal of our covariance matrix, we would have our standard errors squared. So now to derive our standard errors, we just can calculate the square roots of the diagonal elements. And that's what we will do. First of all, for our constant, the estimator would be the square root of the very first element of the matrix. And if we drag it across, we'll get the square roots of the first row. But we need to calculate the square roots of the first diagonal. So what we can do here is we can change the references here to refer to the diagonal, just increasing the row reference by 1 each time. And here, that's how you get the standard errors for the coefficients. Now, we can use the assumption that in large samples, the distribution of coefficients is approximately normal. So, dividing the coefficients by the standard errors, we get z-stats, our usual and well-behaved z-stats that can be tested for significance using a two-tailed t-test. So 2 times 1 minus standard normal distribution. As arguments, we input the absolute value of our z-stat and 1 for cumulative. And here we can get our p-values for every single coefficient. And here we can see that the most significant of the predictors of default are being full-time employed. So if you are employed full-time, you're much less likely to default on your consumer credit. And also the significant positive predictors of default are leverage and repayment time given income. The more leveraged you are, the less likely you are to repay, and the more it would take you to repay your loan out of your income, the less likely you are to repay. While 3 other parameters, the constant, and most notably home ownership and expense to income ratio, are of expected science, but not as significant as one could imagine, given these p-values are greater than 10%. And now we can use our Logit model to actually predict whether a particular individual would default. Imagine we have got this model up and running in our bank, and someone approaches us and asks out for a loan. So we, in our credit scoring procedure, ask them to provide some data about them. So obviously the constant would be 1, as it's always 1, that's why it's a constant. And we ask the applicant whether they own a home, and imagine they say yes, and we put 1 for yes. Then we ask if they have a full-time job, and they say yes and provide some evidence for that. Then to calculate these 3 variables, we need to ask them about their income, expenses, asset, debt, and what is the loan amount they want to apply for. So imagine that this particular person's household makes $150,000 per year, and they spend roughly $120,000 of it. They own their home, and it's currently valued at $1,000, so $1 million, and they haven't got any debt taken on previously. And they want to take out $1 million in loan, potentially guaranteed as collateral by their property, by their house. So now we can actually just copy these formulas across to calculate these ratios, and we can also copy this across to calculate our Logit, and our probability can be calculated just like that. And we can see that our probability, which is Logit divided by 1 plus Logit, is less than 20%. So actually, we can be reasonably sure that such a person would not default on their loan, their default probability being less than 20%, 19.19%, which is quite good, which is also less than average. Over here, we can see that roughly a quarter of our applicants default, and the probability of this applicant defaulting is less than 20%. So we can determine that our applicant is actually creditworthy and feel quite good about providing them with a loan. And that's all there is for the Logit model and its application for consumer credit risk, credit scoring, and much more. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, economics, or finance you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.